We're finishing off chapter 11 with 11.5 colloids. So in this chapter, we're going to describe the composition and properties of colloidal dispersions and list and explain several technological applications of colloids. So let's start by talking about what a suspension and what a colloid are. So suspensions are heterogeneous mixtures comprised of relatively large particles that are visible, or you can see them with a magnifying glass. These are very cloudy, and the particles are going to settle out after mixing. So an example is like putting sand in water and shaking it up. You can see those individual particles of the sand, and you let it sit down, and eventually that sand is just going to settle all to the bottom. So the next thing are colloids, and that's what this whole chapter is focused on. These can also be called colloidal dispersions, and these have properties that are intermediate between those of suspensions and solutions. So they have larger particles than most simple molecules, but they're small enough that they won't settle when you leave your, for instance, water and sand. You have really, really small particles of sand, for instance. They're bigger than a molecule, but they don't settle upon standing. Or milk, for instance. They scatter light in a phenomenon called the Tyndall effect. So this might make them look cloudy or opaque. Some example, like it might look like searchlight beams. Clouds, for instance, are colloidal mixtures because they have water droplets much larger than molecules, but are small enough they don't settle out. And trust me, I could go all about clouds. So most or many colloids have hundreds or thousands of molecules in them, but they can also have a single very large molecule like a protein or a polymer. So yeah, you can have proteins which are massive and have a bunch of amino acids that make them up, where one protein strand can be an entire colloid. Similar to a solution, we have a particulate component and the substance that the colloid is dispersed in. The particulate component can be called the dispersed phase, and the substance that it's in is called the dispersion medium. And we can have pretty much any combination of physical states. Just some examples. A solution is a homogeneous mixture that appears clear, such as salt water in that aquarium in A. B, milk is a colloid. The particles are much larger but stay dispersed in the milk. They don't settle. And then suspensions like mud is heterogeneous. You've got these big suspended particles that make it look cloudy, and they can settle. My family has this great picture of me as a kid playing in the mud because my mom was like, whatever, she's going to get dirty anyway. And I'm covered up to my elbows in mud, smiling the biggest smile a kid can smile. And then they just rinsed me off with the hose. So the passive searchlight beams are made visible when light is scattered by colloidal sized particles in the air. So you've got these colloids in the air, and when the light hits it, they scatter them, which is why you're able to see beams of light. And here's some just examples of some colloidal systems. I'm not going to go through all these, but aerosols are the ones that are close to my heart, because you have liquid and solids, but they're going to focus on liquids dispersed as the dispersed phase, dispersed in a gas to make clouds, fogs, mists, sprays, and we call them aerosols. So colloids are prepared by making particles of colloidal size and dispersing throughout your medium. You can make them of colloid size by dispersion methods, so you break down bigger particles into smaller ones, or by condensation methods, where they grow from smaller units, not so smaller units, such as molecules or ions. So I used to study cloud condensation nuclei. So colloids would be made of cloud droplets by a seed of some type of particulate matter that water condenses on, and it grows until it keeps getting water until it's able to grow into a droplet. We can form emulsions. So emulsions you may have heard of if we shake or blend two immiscible liquids. So what happens when you do this is you're breaking one of those liquids into colloid-sized droplets, which then disperse into the other liquid. These can coalesce, meaning they form large drops and separate. So like oil and vinegar, you shake it up to get them to make an emulsion, but then eventually one of them, you get those big bubbles kind of at the interface and they separate out. You can add an emulsifying agent to keep it from coalescing. Some example, if you put soap in an emulsion of kerosene and water, you can keep it, that would be an emulsifying agent. Milk is an emulsion of butter, fat, and water, and the protein casein is the emulsifying agent. Mayonnaise is an emulsion of oil and vinegar, with egg yolk being the emulsifying agent. We also have, with condensation methods, we form colloidal particles by aggregation of molecules or ions. So like I was saying, with cloud condensation nuclei, we have that water aggregating until it forms a colloid. But if it gets too big, you form drops or precipitates, and then you end up not having a colloidal system. So if that cloud droplet or gets too big, then we get rain. Next, we have soaps and detergents. If you have a salt of a fatty acid, these are called soaps. So the chemical reaction to make them is called saponification. This is not in your book. This might be an extra credit question of some sorts. So the way these are made is you take some fatty acid, either an oil or fat. So when you have olive oil soap, that was your fatty acid, was olive oil. Back in the old day, pioneers would take animal fat. And then you mix it with a strong base such as potassium carbonate, which you get from wood ashes with hot water. But nowadays, sodium hydroxide is used more often, or potassium hydroxide. And this reacts with it in saponification to make a soap. I have made soap for a class that I taught when I did an intro chemistry course at Fullerton College. It is not a nice smelling process. The only reason soaps smell good is because they add things to it. But the process of saponification itself smells awful. There's actually history of people who might live by a soap making plant complaining about the smells. It is disgusting. So the structure of soaps, and we'll look at them on the next slide, you have this very, very large, uncharged, nonpolar hydrocarbon tail. So you have these carbon groups just chained. And then at the very, very end of it, you have this polar group that's a carboxylate group. And we'll see what that looks like in a minute. And then we have detergents, which are used as soap substitutes, that instead of the polar carboxylate group at the head, it has a polar sulfate or sulfonate group at the head instead of carboxylate. The way that soaps and detergents work is the polar end of them is attracted to water, and the nonpolar is attracted to other nonpolar substances like oil or grease. So when you get oil on your hands, you really soap up and the grease goes away, right? That's because that nonpolar tail of the soap is grabbing onto that oil and pulling it out, and then it forms a colloid where all the nonpolar tails, so this is a cross section, you have all the nonpolar tails coming together, and then on the end are all your polar heads that then allows it to interact with water and be washed away. So here's an example of sodium stearate. This is one type of soap. And this long chain, what this chain is what determines what type of soap you have. All of them have this carboxylate end. So what it looks like is you have a carbon with a double bond to oxygen, then another oxygen here with a negative charge and Na+. So it's actually an ionic head as well. So you've got that negative positive. So it's an ionic polar head. And then here's sodium lauryl sulfate. This is an example of a detergent. Same type of thing, you've got that ionic polar head, just now with sulfate instead of carboxylate. And this is this is a cross-section of what a drop of oil and water shows when you have soap. It acts as an emulsifier, so they mix together. Okay, the oil ends up being in here, in this whole tan area, and then you have the polar head that's then able to interact with the water. The Deepwater Horizon oil spill, awful, April 20th, 2010, the Gulf of Mexico. To date, this is the largest marine oil spill in the history of the petroleum industry. 4.9 million barrels or 210 million gallons of oil flowed into this ruptured well 5,000 feet below the water's surface. It wasn't sealed until September 19th, 2010. Crude oil is immiscible with water, but it's also less dense, so it rose to the surface of the water. And so a lot of different ships and floating blooms and all these things were used to try to remove oil from the surface to protect the beaches and wetlands. And they were trying to make it soluble so it would kind of dissolve in the water and have less harmful levels. But it was still really, it was bad. Very, very, very bad. All right, moving on. Just kind of quick about electrical properties of colloidal particles. Dispersed colloidal particles are often electrically charged, but every single colloidal particle will have the same charge and the same sign. So this is a good thing because like charges repel each other. So then they're kind of trying to stay away from each other. And we can use that charge to also remove them from mixtures. Frederick Cottrell actually developed the electrostatic precipitator, which is sometimes used to curb air pollution to take some colloidal particles from the air. Okay, so these might be used especially for things like soot. Soot's bad. It can really screw up your lungs. So gels, this is the last part of the chapter. These are a type of colloid where aqueous mixture coagulates as it cools, making a viscous body. So Jello, pectin, silica gel, those canned heat flammable gel canisters that are used like at buffets, these are all examples of gels. So the fibers of the dispersing medium form this complex three-dimensional network with the interstices filled with either liquid medium or dilute solution of the dispersing medium. So here's gelatin. So they are colloids in which aqueous solutions of sweeteners and flavors is dispersed throughout a medium of solid proteins. So gelatin, most people know this by now, is not a vegetarian product. It's actually derived from bone marrow of animals. So if you have a friend who's vegetarian or vegan, do not give them Jello. And that does it for Chapter 11 and our lectures for Chem 2A. Of course, there'll be announcements and stuff throughout the week and next week. But I just want to go ahead and say it's been a pleasure. I'm very proud of all you guys. You've made it through all the lectures. Let's finish strong.